Welcome to 6502 Assembly Language Programming. In this video, we'll look at multi-byte shift operations. Why do we need multi-byte shift operations? 6502 arithmetic operations operate on 8 bits at a time. But depending on the program we are writing, we may need to work with larger numbers, such as with game scores, bank balances, geographic distances, for instance. The 6502 also does not have hardware multiplication or division. And when implementing those operations in software, we'll have to do some shifting. The idea of all multi-byte operations is to operate on 1 byte at a time while using the carry flag to propagate information from 1 byte to the next. These slides show the operation of a short snippet of code performing a multi-byte operation. The big white arrow represents the program counter. The table represents the state of the carry flag and 3 variables in storage. The values are all represented in binary. CLC is the clear carry instruction. So the carry flag is set to 0 and the program counter advances. The ROL is the rotate left instruction. It will shift all the bits in the target left, shifting the carry flag into the low order bit and the high order bit into the carry. Here, we aren't shifting the bits in a register, but directly in memory, a very useful capability. After the first ROL instruction, byte 0 is rotated left with the contents of the carry flag rotated into bit 0 of byte 0, and the contents of bit 7 of byte 0 rotated into the carry flag. The second ROL works in the same manner as the first, but with byte 1 as its target. At the start of execution, the carry flag contains what had been the contents of the most significant bit of byte 0, which will be rotated into bit 0 of byte 1. After execution, the carry flag will contain the contents of bit 7 of byte 1. After the third ROL, we've completed the multi-byte shift and only need to deal with the bit that has been rotated out of the high order bit of the 24-bit value. Okay, let's go see this in operation in the IDE. Before continuing this video, if you are not familiar with 8 bits in 1 byte or don't know how to use its IDE, you will find helpful links in the description below about using the IDE, its debugger, and how to save and load your work. Okay, let's go to the 8 bits in 1 byte website to have a look at the exercise associated with this video. You'll find a link to this page in the description. So I'm going to click Resume Work since I saved my previous work. And here we're going to look at ex8.asm. And here our task is to shift the value in param underscore 0, 1, and 2 to the right 1 bit. We have to shift the 0 into bit 7 of param 0. And the outputs of exa8 will be the shifted values in memory, and the single low order bit of output 0 representing the final value of the carry flag after shifting param 2. And it shows what the before and after should look like. Okay, so you should have a pretty good idea about how to solve this. based on the material we've just looked at. So now would be a good time to pause and have a try at it. Okay, well, welcome back. Let's go ahead and look at my solution. As you can see, it's only a few lines of code, but let's walk through it. First of all, I clear the carry flag so that when we do this rotate right, it'll be rotating a 0 into the upper bit of param 0. So we go through one pass here, we do a rotate right on param 0, do another rotate right on param 1, and then param 2. Very simple. And so the low order bit of param 0 is rotated into the carry flag, which is then rotated into the upper bit of param 1 as a part of this shift operation, and so on with param 2. So after this final shift, we need to do something with the carry flag so we can save it in output 0. Save that one bit in output 0. So we're going to do something a little bit fancy. We're going to push the processor status word onto the stack. That's what's happening here. And then we're going to pull that value off the stack into the A register. And it turns out the format of the processor status word is such that it's the low order bit that is the carry flag. And so we just store that in output 0 and we'll declare ourselves done. And so we load X with the immediate value implemented to signal that to the test code. So let's go ahead and run that. As you can see, our exercise solution appears to have worked since we have a nice green light next to the R. Let's go ahead and step through EX8 to see if there's any more to be learned. I'll set a breakpoint here, and we'll stop at the CLC instruction. Opening up the CPU tab. Now, the PSR is over here. I hope you can see my pointer. And you can see right now the carry flag is set to 1. So after stepping through the CLC, it'll be set to 0. And now we're going to do our rotates. Now, since these rotates are not in registers, we have to look at the memory locations. And you can see they're at 80, 81, and 82. So let's go ahead and bring up memory. So to begin with, 80 is 55. Well, they're all 55. So 80, 81, and 82 right there. I'm gonna make that bigger. Make everything bigger so it's easier to see. So let's go ahead and shift. See what happens there? You can see location 80 is now 2A. And what's in the carry flag? It's 1. So you can see it here. You can also see it here. And let's keep shifting. And now location 81 is now AA. And we'll keep shifting. Location 82 is also AA. And now we're going to try to access the carry flag as we described. So we'll go ahead and push this onto the stack. You'll see it pop up over here. This is where the stack is. Stack pointer is F8. That is here. So I think this Baker 5 is the value we just pushed on. Okay, so let's go ahead and actually we didn't need to do that. We're just going to pop it off anyway into the A register. So let's look. So here in the A register we have Baker 5, which has 1 in the low order bit. And so we're just going to store that in output 0 and claim the exercise is completed. Now I do want to say that it would have been cleaner if I had masked off this low order bit before storing the A register in output 0. So let's improve our solution a little bit and mask off these extraneous bits. As you can see, right now we have Baker 5 in the A register. We want to mask off every bit except the low order bit. So after our improvements, it should just be 1 instead of Baker 5. So back to the source we go. And here we're going to add a line of code and say AND against an immediate value of 1. We'll say mask extraneous bits. So we'll run that, and here is our new instruction there. Let's put a breakpoint down here and resume. And now in our A register we have 1. So we've improved it a little bit, our solution. So let's remove all our breakpoints. Hit resume. And just note again that we have a nice green light here next to the R. Thanks very much for watching this video all the way to the end. I hope you enjoyed it and derived some benefit. If you did, please click like and subscribe. Thanks very much and have a great day.